You cannot share a neutral with other phases regardless of whether a ground fault circuit interrupter breaker is involved. A ground fault circuit interrupter breaker trips when it detects an imbalance in current between the hot and neutral conductors. This imbalance occurs when current is leaking to ground. Sharing a neutral between phases would defeat the purpose of the ground fault circuit interrupter breaker. If current were to leak to ground on one phase, the ground fault circuit interrupter breaker on that phase would not trip because the neutral would allow current to return to the other phases. Therefore, each phase must have its own separate neutral conductor. This ensures that the ground fault circuit interrupter breaker can properly detect ground faults on its own phase. Let's delve deeper into the reasons why sharing a neutral with other phases is not permissible when using ground fault circuit interrupter breakers, focusing on electrical safety, code compliance, and practical implications. Firstly, understanding the fundamental principle of a ground fault circuit interrupter breaker is crucial. A ground fault circuit interrupter breaker is designed to protect individuals from electrical shock by monitoring the current balance between the hot, or line, conductor and the neutral conductor. In a standard electrical circuit, the current flowing through the hot conductor should equal the current returning through the neutral conductor. If there's a difference, even a small one, typically around 5 mA, the ground fault circuit interrupter breaker interprets this as a current leakage to ground, indicating a potential shock hazard. It then quickly trips the circuit, interrupting the flow of electricity. Secondly, the problem with sharing a neutral lies in how it disrupts the ground fault circuit interrupter breaker's ability to accurately monitor this current balance. When multiple phases share a single neutral, the neutral conductor carries the combined return current from all those phases. If a ground fault occurs on one phase, the fault current may return through the shared neutral, but it will be mixed with the normal return current from the other phases. The ground fault circuit interrupter breaker in the phase with the ground fault may not detect the imbalance because the fault current is masked by the other phase's return currents. This compromises the ground fault circuit interrupter breaker's ability to trip and protect against electrical shock. Thirdly, electrical codes such as the National Electrical Code explicitly prohibit sharing a neutral in circuits protected by ground fault circuit interrupter breakers. These codes are in place to ensure safety and prevent electrical hazards. Violating these codes can lead to dangerous situations and potential legal repercussions. Consult the latest edition of the National Electrical Code for specific requirements and restrictions related to ground fault circuit interrupter breaker installations and neutral conductor sharing. Understanding the applicable codes is paramount for safe and compliant electrical work. Fourthly, consider a practical example to illustrate the issue. Imagine a three-phase system where each phase is feeding a separate load, and all three phases share a single neutral conductor. If a ground fault occurs on one of the phases, say phase A, the fault current will travel through the shared neutral along with the normal return currents from phases B and C. The ground fault circuit interrupter breaker on phase A will see a combined current that may not exceed its trip threshold, even though a dangerous ground fault is present. The result is a potentially hazardous situation where the ground fault circuit interrupter breaker fails to provide the intended protection. Fifthly, the solution is straightforward. Each phase must have its own dedicated neutral conductor that is not shared with any other phase. This ensures that the ground fault circuit interrupter breaker on each phase can independently monitor the current balance and trip if a ground fault occurs on that specific phase. Using separate neutral conductors is a fundamental principle of ground fault circuit interrupter breaker installation and is essential for proper operation and safety. Sixthly, when installing or modifying electrical circuits, it is imperative to verify that the wiring configuration complies with all applicable codes and standards. This includes ensuring that neutral conductors are properly sized, insulated, and connected. Incorrect wiring can create hazardous conditions and compromise the effectiveness of safety devices like ground fault circuit interrupter breakers. If you are unsure about any aspect of electrical work, it is always best to consult with a qualified electrician. Seventhly, it is important to note that the prohibition of shared neutrals with ground fault circuit interrupter breakers applies to both residential and commercial electrical systems. Regardless of the application, the principle remains the same. Ground fault circuit interrupter breakers require dedicated neutral conductors to function correctly. Neglecting this requirement can have serious consequences. Eighthly, in addition to the safety concerns, sharing a neutral can also create other problems such as voltage imbalances and harmonic distortion. These issues can negatively impact the performance of electrical equipment and lead to premature failure. Using dedicated neutral conductors helps to minimize these problems and ensures a more stable and reliable electrical system. Ninthly, when troubleshooting electrical circuits, it is crucial to inspect the wiring for any signs of shared neutrals or other improper connections. This can be done using a multimeter or other appropriate testing equipment. If any issues are found, they should be corrected immediately to prevent potential hazards. Tenthly, remember that electrical work can be dangerous if not performed correctly. Always take the necessary precautions, such as wearing appropriate personal protective equipment and energizing circuits before working on them. If you are not comfortable working with electricity, it is best to leave the job to a qualified electrician. In summary, the prohibition of sharing neutrals with ground fault circuit interrupter breakers is a critical safety requirement that must be strictly adhered to. Doing so ensures that ground fault circuit interrupter breakers can effectively protect against ground faults and prevent electrical shock. Understanding the reasons behind this requirement, along with proper wiring practices, is essential for maintaining a safe and reliable electrical system. Let's elaborate further on the technical aspects and implications of not sharing neutrals with ground fault circuit interrupter breakers. Firstly, consider the impact on harmonic currents. In modern electrical systems, nonlinear loads such as electronic devices, computers, and LED lighting can generate harmonic currents. These currents are multiples of the fundamental frequency, typically 60 Hz, and can cause various problems, including overheating of neutral conductors, transformer overloading, and voltage distortion. When multiple circuits share a neutral, the harmonic currents from each circuit add together in the neutral conductor. This can lead to a significant increase in the neutral current, potentially exceeding the conductor's ampacity and causing it to overheat. The National Electrical Code specifies requirements for neutral conductor sizing, particularly in systems with significant nonlinear loads, to address this issue. In systems where ground fault circuit interrupter protection is required, sharing a neutral exacerbates the problem by potentially masking ground faults and increasing the risk of neutral conductor overload. Secondly, let's discuss the concept of multi-wire branch circuits. A multi-wire branch circuit consists of two or more ungrounded conductors that have a voltage between them, and a neutral conductor that has equal voltage between it and each ungrounded conductor of the circuit, and that is connected to the system neutral or grounded conductor. Multi-wire branch circuits can be an efficient way to distribute power, but they must be wired correctly to ensure safety. The National Electrical Code permits the use of multi-wire branch circuits under certain conditions, but it also imposes restrictions to prevent overloading the neutral conductor and compromising ground fault circuit interrupter protection. Specifically, the code requires that the neutral conductor in a multi-wire branch circuit be sized to carry the maximum unbalanced load. Furthermore, the code prohibits the use of multi-wire branch circuits to supply more than one appliance or luminaire on the same yoke, unless each device is individually protected by a ground fault circuit interrupter breaker. Thirdly, let's examine the role of impedance in ground fault circuit interrupter breaker operation. Impedance is the total opposition to current flow in an alternating current circuit, and it consists of resistance, inductive reactance, and capacitive reactance. When a ground fault occurs, the fault current flows through the ground path, which typically has a relatively high impedance. This impedance limits the magnitude of the fault current, but it may not be high enough to trip a standard circuit breaker. Ground fault circuit interrupter breakers are designed to detect even small ground fault currents, typically in the range of 5 mA, by monitoring the current balance between the hot and neutral conductors. The ground fault circuit interrupter breaker's internal circuitry is highly sensitive and can detect minute differences in current flow. When a ground fault is detected, the ground fault circuit interrupter breaker quickly trips, interrupting the circuit and preventing electrical shock. Fourthly, consider the impact of voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can negatively impact the performance of electrical equipment and cause it to operate inefficiently. Sharing a neutral can increase voltage drop, particularly in long circuits or circuits with heavy loads. This is because the shared neutral conductor carries the combined return current from multiple circuits, increasing its current carrying requirements and its impedance. To minimize voltage drop, it is important to use appropriately sized conductors and to avoid sharing neutrals. Fifthly, let's discuss the importance of proper grounding. Grounding is the process of connecting electrical equipment and circuits to earth, providing a low impedance path for fault currents to flow back to the source. Proper grounding is essential for electrical safety, as it helps to prevent electrical shock and to protect equipment from damage due to overvoltages. The National Electrical Code specifies detailed requirements for grounding electrical systems, including the types of grounding electrodes, the size and installation of grounding conductors, and the bonding of metallic enclosures. When ground fault circuit interrupter protection is used, proper grounding is even more critical, as it ensures that ground fault currents can flow back to the source and trip the ground fault circuit interrupter breaker. Sixthly, let's examine the role of surge protection. Surge protection devices are designed to protect electrical equipment from damage due to voltage surges, such as those caused by lightning strikes or power line disturbances. Surge protection devices work by diverting the surge current to ground, preventing it from reaching sensitive equipment. While surge protection devices can help to protect against overvoltages, they do not provide protection against ground faults. Ground fault circuit interrupter breakers are specifically designed to protect against ground faults, and they should be used in conjunction with surge protection devices to provide comprehensive electrical protection. Seventhly, let's discuss the importance of regular testing of ground fault circuit interrupter breakers. Ground fault circuit interrupter breakers should be tested regularly to ensure that they are functioning correctly. The National Electrical Code recommends that ground fault circuit interrupter breakers be tested monthly using the test button on the device. This test simulates a ground fault and verifies that the ground fault circuit interrupter breaker trips as expected. If a ground fault circuit interrupter breaker fails to trip when tested, it should be replaced immediately. Eighthly, let's consider the impact of electromagnetic interference. Electromagnetic interference is the disturbance caused by electromagnetic fields that can interfere with the operation of electronic equipment. Electromagnetic interference can be generated by various sources, including electrical wiring, electronic devices, and radio transmitters. Sharing a neutral can increase electromagnetic interference, particularly in circuits with high-frequency components. This is because the shared neutral conductor can act as an antenna, radiating electromagnetic energy. To minimize electromagnetic interference, it is important to use shielded cables and to avoid sharing neutrals. Ninthly, let's discuss the importance of proper labeling of electrical circuits. Electrical circuits should be properly labeled to identify their purpose and their voltage. This helps to prevent confusion and to ensure that electrical work is performed safely. The National Electrical Code specifies requirements for labeling electrical circuits, including the use of circuit directories and the identification of circuit breakers. When ground fault circuit interrupter protection is used, it is important to clearly label the circuits that are protected by ground fault circuit interrupter breakers. Tenthly, let's remember that electrical safety is paramount. Always take the necessary precautions when working with electricity, such as wearing appropriate personal protective equipment, de-energizing circuits before working on them, and following all applicable codes and standards. If you are not comfortable working with electricity, it is best to leave the job to a qualified electrician. In conclusion, the prohibition of sharing neutrals with ground fault circuit interrupter breakers is a critical safety requirement that must be strictly adhered to. This ensures that ground fault circuit interrupter breakers can effectively protect against ground faults and prevent electrical shock, while also minimizing other potential problems such as harmonic currents, voltage drop, and electromagnetic interference. Understanding the reasons behind this requirement, along with proper wiring practices, is essential for maintaining a safe and reliable electrical system.